Imagine deploying an autonomous coding agent on a Monday to refactor, a sprawling microservices architecture.
Right, a massive code base.
Yeah. And by Wednesday, it's doing fine. It's navigating complex dependencies. But then by Friday, it's suddenly crashing your servers.
And it's crashing them because it keeps pulling up a deprecated API schema from Tuesday.
Exactly. It's trapped in this computational loop, continuously rediscovering the same directory layout and making the exact same errors. So why does this happen?
Well, because while the neural weights of our foundation models are just brilliant at mapping an input sequence to a probability distribution, the model itself is fundamentally stateless.
Right. It's just a stateless function.
Exactly. And the moment you push an LLM to act as an autonomous agent over long horizons, that statelessness becomes a fatal flaw. Its memory is effectively a disorganized, degrading sticky note.
Which means we really need to reevaluate what memory actually is in the context of an agent, right? Welcome to today's deep dive. If you're building or researching LLM agents, memory isn't just a database engineering problem where we append strings to a prompt.
Or just dump documents into a vector index, yeah.
Right. Today we're digging into a comprehensive 2026 survey by Pengfei titled Memory for Autonomous LLM Agents: Mechanisms, Evaluation, and Emerging Frontiers. Our mission here is to unpack how memory transforms these stateless text generators into adaptive agents.
And we are talking complex, mathematically rigorous, multi-tiered systems evaluated by active agentic utility, not just, passive recall.
Right, and what I love about this paper is how it hooks you immediately by framing the core problem mathematically. It formalizes the LLM agent loop as a partially observable Markov decision process, or a POMDP.
Which is such a crucial framing. Because in a classical POMDP, the true state of the environment, say, the complete real-time status of a millions of lines code base is entirely unobservable.
Right, the agent can't see the whole board.
No, it only receives localized, incomplete observations, like just seeing the terminal output of a single grep command.
So to survive in a POMDP, the agent has to maintain a belief state. And for you listening, that is the core premise we are unpacking today. Memory, which we'll denote mathematically as M sub t, is essentially that belief state.
It acts as a sufficient statistic of the entire interaction history.
Exactly. It stands in for the unobservable true state of the world. It's a continuously updating mathematical representation of reality. So if we accept that memory is this dynamic belief state, we need a structural framework, right? How does this update and retrieval process actually operate under the hood?
Yeah, so the agent loop is defined through two highly interdependent functions at any discrete time step. Tenya. The action, a sub t, is determined by the policy pi sub theta.
Okay, the policy.
Right, and this policy takes the current observation x sub t, the active goals g sub t, and critically, the output of a read function from memory, which we denote as r of m sub t and x sub t.
Got it. But the real complexity sits in the write and manage function, doesn't it?
Oh, absolutely. The new memory state, m sub t plus 1, is produced by an update operator, u, and this u operator takes in the previous memory, m sub t, the input x sub t, the action taken a sub t, the resulting observation o sub t, and the environment reward r sub t.
Right, and I think it's so important to point out that U mathematically cannot just be a linear array append operation.
Oh no, if it were, your state space would grow unboundedly.
Yeah, you'd saturate the context window or hit retrieval latency constraints almost instantly.
Exactly. U has to be this highly nonlinear operator. It has to handle summarization, deduplication, priority scoring.
Contradiction resolution,
Well,
deletion, all of it.
right, because the policy pi sub theta and the read-write functions form a recursive feedback loop. So a single erroneous write operation at step 10 can pollute the entire belief state.
Creating a cascading failure that just derails the policy for hundreds of downstream steps.
Exactly. And categorizing how different architectures implement that nonlinear U operator reveals a three-dimensional taxonomy in the paper.
Let's break that down. The first dimension is temporal scope, right?
Yeah, temporal scope, which functionally mimics human cognitive architecture, but uses distinct data structures. You have working memory, which maps directly to the active transformer context window, the KV cache.
Right, the immediate context.
Then you have episodic memory, which operates as an append-only log. It stores concrete, timestamp interactions and specific tool calls.
Like a raw feed.
Exactly. Then semantic memory, which strips away the temporal context to store abstracted, deduplicated knowledge. And finally, procedural memory, which houses reusable skills.
Usually encoded as executable scripts or verified subroutines, right? Like The school libraries from Voyager.
You got it.
I find the transition from episodic to semantic memory fascinating. It functionally mirrors the transition from logging raw, high-variance streaming data to actually training a generalized model on that data.
That's a great way to put it.
You take isolated episodic data points, like a user correcting a date format on Monday and then correcting it again on Thursday, and the U operator consolidates them into a semantic rule, like this environment strictly requires ISO 8601 formatting.
Right, but consolidating a natural language episode into a structured rule requires complex schema mapping. It's not just a simple gradient descent update.
Which brings us to the second dimension, the representational substrate.
Yeah, the substrate dictates the actual data structures underlying those temporal scopes. So memory can be context-resident text, meaning it lives entirely in the prompt.
Sure.
It can be vector index embeddings stored in something like Face or Milvis. It can be structured relational tables managed via SQL, or executable code repositories for procedural skills, or, a hybrid of all these.
And the difficulty of semantic consolidation really comes down to translating across these substrates, right?
Yeah. Oh, massively. Moving an observation from a text-based episodic log into a structured SQL semantic memory requires the agent to perfectly extract entities and relations without hallucinating schema properties.
Which is incredibly hard. And the mechanism that dictates how information moves across these scopes and substrates is the third dimension, which is the control policy.
Right. Historically, architectures relied on heuristic control, just hard-coded rules triggering a summarization script every 1,000 tokens.
Or retrieving the top's nearest neighbors on every single turn.
Exactly. Then the field shifted to prompted self-control. This gave the LLM memory operations as callable tools, letting it decide when to search or write based on its system prompt.
But heuristics and prompted tools are brittle, which forces us to look at the specific failure modes of these systems in deployment. Let's dive into that. Context-resident memory seems to be the most fragile.
Without a doubt, when you compress a rolling window of text to stay within a token limit, you trigger summarization drift.
Because the U operator keeps discarding low-frequency signals.
Right. Over time, the agent retains this highly sanitized, generic representation of the interaction history. Meanwhile, the rare but critical constraints just vanish from the belief state.
And even if you just throw compute at it and expand the context window to, say, 200,000 tokens to avoid summarization entirely, you hit attentional dilution.
Yes. The attention mechanism's capacity is distributed so thinly across that massive sequence length that the model fails to appropriately weight the critical tokens.
The classic lost-in-the-middle phenomenon, which naturally forces engineers toward non-parametric external substrates. So retrieval-augmented generation, or a RAG, becomes a default.
It does, but standard dense retrieval introduces massive bottlenecks when operating autonomously. Just dumping unstructured logs into a vector database and running cosine similarity searches is highly inefficient for an agent.
Right, the technical sweet spot requires multi-granularity indexing. If your chunking strategy is too fine, you shatter the multi-step reasoning traces necessary for agentic planning.
And if you chunk too coarsely, your signal-to-noise ratio just plummets, and the read function pulls in thousands of irrelevant tokens.
Plus, the immediate unedited observation, x sub t, is almost never the optimal query vector anyway.
Exactly. State-of-the-art implementations now rely on query reformulation and entropy-based gating. Frameworks like self-RAG use a dedicated classifier to evaluate the entropy or uncertainty of the current belief state.
So it actively calculates whether the current task actually warrants a retrieval operation.
Right. It bypasses the latency of a vector search entirely if the internal parametric knowledge is sufficient.
That makes a lot of sense. Now, moving beyond basic RAG, we see architectures attempting to emulate human reflection. Systems like reflection or generative agents introduced reflective memory, where the agent generates verbal self-critiques after failing a task and appends those to its semantic memory.
It sounds great in theory.
But mathematically, there's a massive risk here of self-reinforcing errors, right? If an agent fails to authenticate an API just because of a temporary network timeout, and it writes a heuristic reflection stating API X is permanently broken,
You are overfitting the policy to a single out-of-distribution failure. Yes.
exactly. The agent creates a false constraint in its belief state that it will never violate and therefore never correct.
Overgeneralization is definitely the primary vulnerability of reflective memory. A single hallucinated reflection permanently poisons the belief state because all future actions are conditioned on it.
So how do we fix that?
The architectural mitigation for this is reflection grounding. This enforces a constraint on the update function, where any generalized reflection must cryptographically, or at least verifiably, cite multiple episodic evidence records.
Oh, wow. So if the agent proposes a new semantic rule, the U operator requires it to traverse its episodic log and link, say 3 distinct, temporally separated failures that prove the rule.
Exactly. It acts as a regularization term on the memory update. It drastically reduces the variance of the reflection.
That's brilliant. But I also see severe limitations in hierarchical memory architectures. You look at systems like memGPT, which map context windows to RAM, vector databases to disk, and cold storage to archival drives. They're effectively building an OS-level virtual memory pager.
Right. It's an elegant architecture.
It is elegant, but the danger in a natural language space is silent orchestration failures. In a traditional operating system, if a paging algorithm drops a critical page, the system throws a precise page fault error.
You know exactly what went wrong.
Right. But in these LLM architectures, if the heuristic policy evicts a critical user constraint to cold vector storage just to save tokens, it doesn't throw an error. The agent just silently generates a suboptimal action, and the downstream reward degrades without any clear traceback.
It is a fundamental observability crisis, and the inability to assign credit or blame to a specific heuristic memory eviction is exactly why the 2026 frontier has migrated to learned control.
Learn and control.
Yes. The most prominent example is agentic memory, or AgeMem, which just abandons heuristics and prompted tools entirely.
Interesting.
Instead, it treats the memory operations themselves, read, write, summarize, and delete, as discrete reinforcement learning actions within the environment.
We have to unpack the mechanics of that,
Yeah.
because treating a database write as an RL action requires a massive shift in how we train the controller, right?
Absolutely. AgeMem optimizes these actions end-to-end using stepwise group relative policy optimization, or GRPO.
Okay, GRPO, how does that work in this context?
GRPO works by sampling multiple trajectories or groups of actions for the exact same prompt. It evaluates the relative advantage of a specific sequence of memory operations against the other sequences in that group.
So it provides dense, step-level credit assignment.
Yes, the credit assignment is the real breakthrough here. By propagating the final task reward back through the specific sequence of memory operations, the controller actually learns non-obvious, highly efficient memory management strategies.
Like what?
Well, the learned policy will proactively trigger a summarization action at step 15, well before the context window is full.
Why?
Because the value function anticipates a highly complex reasoning task at step 20 that will require maximum available token bandwidth.
Oh, that's incredible. The model learns to dynamically manipulate its own belief state to maximize the expected return, balancing the token cost against the informational value.
Exactly.
But wait, this level of dynamic manipulation completely breaks traditional information retrieval evaluation metrics. We have to address a really difficult question here. How do we mathematically evaluate an agent's memory when passive recall metrics just no longer correlate with task success?
It's a huge problem.
If we evaluate the read function R using classical metrics like precision at K or normalized discounted cumulative gain, NDCG, we are basically assuming that relevance is a static property. But in an autonomous agent, relevance is highly dynamic, conditioned on that unobservable true state.
Right. Classical metrics are functionally blind to the temporal realities of an agentic environment. They completely fail to account for staleness.
Staleness is a huge issue.
Yeah. If an agent retrieves a configuration file from 2024 instead of the updated 2026 version, an NDCG score might still rate that retrieval highly, just based purely on the semantic cosine similarity between the query and the document.
But for the agent's actual execution path, retrieving the stale document is a catastrophic failure.
Exactly. Traditional metrics also fail to penalize contradictions between chunks, and they completely ignore the operational latency of the retrieval process.
So the evaluation paradigm has shifted to a new suite of benchmarks designed for active utility. You have Locomo, which tests massive long-term conversational memory spanning up to 35 separate sessions.
Yep.
You have MemBench, which isolates the evaluation of factual retrieval from the evaluation of generalized reflective memory. But I think the most revealing is Memory Agent Bench, right?
Oh, definitely. Memory Agent Bench grounds its evaluation in cognitive science. It introduces adversarial components. It actively penalizes models that fail at selective forgetting.
So if obsolete information is injected into the context, the model's score degrades if the U operator fails to prune it.
Right, and the empirical findings from these active benchmarks, specifically the interdependent multi-session tasks in memory arena, are stark.
How stark are we talking?
The data reveals that models capable of scoring near perfectly on the passive recall tasks of Locomo see their success rates plummet to 40 or 50% on memory arena.
Wow. Just a massive drop-off.
Yeah, because a decision made in session 3 might depend entirely on synthesizing an implicit constraint from session 1.
For you listening, this drop-off is a classic machine learning trap, covariate shift. It is the exact difference between an algorithm achieving 99% accuracy on a static validation set versus deploying that same algorithm into a live RL environment.
Perfect analogy.
In passive IR, the data distribution is stationary. You ask a question, you get a document. But in active agentic utility, poor memory retrieval at step 2 causes the agent to take a slightly suboptimal action.
And that action changes the environment.
Exactly, which shifts the state distribution of the subsequent observation at step 3. The agent is pushed entirely out of its training distribution, leading to this cascading compounding error. Passive recall simply does not guarantee decision-relevant utility under covariate shift.
It really doesn't. And to bridge this massive evaluation gap, Pengfei Du's research formalizes a 4-layer evaluation stack that systems just have to be optimized against simultaneously.
Let's run through the stack. Layer 1 is task effectiveness, right? Measuring the final success rate, the step count, plan completion.
Yep. And layer 2 goes much deeper into memory quality. We're no longer just looking at similarity. We are actively tracking the staleness distribution of retrieved facts.
Right.
We're calculating the contradiction rate within the belief state and measuring whether the retrieved context strictly covers the necessary preconditions to execute the next tool.
So it's heavily functional.
Very much so. Layer 3 then introduces the physical constraints. Efficiency. It tracks the exact prompt tokens consumed by memory content to ensure the context isn't bloated, and it measures the latency per memory operation.
Which brings us to layer 4, governance, measuring privacy leakage rates and adherence to deletion compliance. And honestly, this is becoming the most critical hurdle for enterprise deployment.
Absolutely.
That governance layer brings us to the severe engineering friction points causing real-world deployments to fail right now. I mean, if the agent is actively overwriting its belief state based on live actions, how do we audit it? Let's look at schema drift.
Schema drift is a nightmare.
Right. An agent's procedural memory stores sequences of verified API calls.
Yeah.
If the external environment updates an API interface, say, changing a parameter name or deprecating an endpoint, all the stored procedural memory suddenly becomes toxic.
Yeah, without version tracking and continuous causal schema validation on the right path, the agent accumulates invalid records and its performance just silently degrades.
And the friction point of unlearning is particularly severe when you compare non-parametric to parametric memory substrates.
Oh, definitely. Non-parametric memory, like the external vector stores and SQL databases, can be audited. You can locate a specific obsolete or restricted data point and just drop the row.
Simple enough.
Right. But parametric memory, where knowledge is fine-tuned directly into the model's neural weights, well, that offers incredibly seamless integration into the reasoning process. But machine unlearning in parametric space is this massive, open, mathematically rigorous problem.
Because you cannot simply delete a node from a weight matrix.
No, you can't. Utilizing Hessian approximations or gradient descent to force a model to forget a concept almost always degrades the surrounding representation space.
Which points perfectly to where the field is heavily investing right now. The paper outlines 3 massive open challenges. The first is principled consolidation. The research points toward a dual buffer consolidation architecture modeled directly after the human hippocampus.
Right, so memories don't just dump into a long-term vector store.
Exactly. They sit in a hot buffer for a probation period. And during this time, they undergo asynchronous re-verification, clustering, and deduplication before being formally promoted to the cold, long-term neocortical storage.
Which is such a biologically elegant solution. And the second frontier is learning to forget. Developing mathematically safe deletion policies that prune the state space without destroying the foundational reasoning pathways.
But the third open challenge is the one I really want to focus on, causally grounded retrieval. Because standard vector similarity is ultimately just a nearest neighbor search in a high-dimensional embedding space. It captures semantic overlap efficiently.
Right, but semantic overlap is completely useless for root cause analysis in an agentic loop.
Exactly. If an agent is debugging a crash microservice, the root cause might be a malformed configuration file that was edited 3 weeks prior. Semantically, the text of a core dump and the text of a config file look absolutely nothing alike.
Their cosine similarity in a dense vector space is basically near zero.
Near zero. So standard Boggle will never retrieve that file. So how do we bridge causal discovery with dense vector indexing? How do we surface a memory that is semantically distant but causally upstream?
The proposed mathematical solution is brilliant. You overlay a discrete causal metadata graph on top of the continuous vector index.
Okay, how does that work?
So during the write operation U, the agent doesn't just embed the observation into the manifold. It runs a lightweight causal estimation to identify the parent node.
Interesting.
It then annotates the new vector record with a directed edge pointing directly to the prior state or action that precipitated it. You are effectively embedding a directed acyclic graph, or a DAG, right into the vector space.
Oh, wow. So at retrieval time, the read function R isn't just performing a dot product. It executes a hybrid traversal algorithm.
Exactly.
It anchors on semantic similarity to find the immediate nodes related to the crash, but then it switches to graph traversal, walking the explicit causal edges backwards in time to locate the root dependency.
Yeah, and even if those causal annotations are just probabilistic estimates generated by the LLM, leveraging that DAGI structure completely shatters the bottleneck of relying purely on semantic proximity.
It represents a beautiful fusion of symbolic AI structures with deep continuous learning. And it really proves that the field is moving far beyond the brute force era of merely expanding the context window to absorb more tokens.
It really is a paradigm shift.
Let's briefly recap the core technical journey we've covered today. We started by discarding the database analogy, formalizing agent memory as the continuously updating belief state M sub t within a POMDP.
We mapped the three-dimensional taxonomy of temporal scope, representational substrate, and control policy.
Right, and we analyzed the shift from static heuristic write rules to discrete RL-optimized control policies using stepwise GRPO.
And we broke down the critical covariate shift that occurs between passive IR recall on static datasets and active agentic utility in interdependent dynamic environments.
Exactly. So to wrap up, where does all this lead?
Well, the long-term trajectory of this research points towards something truly ambitious. A foundation model for memory management.
A foundation model just for memory.
Yes. Imagine a neural architecture explicitly pre-trained not for general linguistic generation or code completion, but solely to act as a universal memory controller.
Oh, wow.
A dedicated routing engine that seamlessly manages the entire write, retrieve, consolidate, and forget lifecycle across diverse agent architectures, basically acting as an agnostic coprocessor for any underlying LLM.
That is a profound engineering challenge. I mean, how do you even design an unsupervised loss function over the entire temporal lifecycle of a belief state? It brings us right back to our opening tension. For you listening, think about this. We are attempting to build mathematical architectures that take the static, binary precision of an algorithmic search and apply it to the messy, interdependent, endlessly compounding reality of an autonomous agent operating in the wild.
We are building systems that don't just passively record the past, but actively synthesize it to navigate the future.
Perfectly said. Keep optimizing, and we will catch you on the next deep dive.